So let's start with the easiest of all exponential functions, the function 2 to the x. So this is where a is 1 and b is 2 in the formula which appeared in the previous video. And let's take a look at what the graph of that function may look like. So we're going to construct a little table with values of x, values of f of x. So I could consider like any real number, but I'm just going to consider the integers. It will be easier to actually compute it by hand. Okay, so I think I have enough. So 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. Over here, this is 2 to the minus 1. So this is 1 over 2, 1/2. This one is 2 to the minus 2. This is 1 over 2 to the 2. So that's 1/4. So on this left-hand side, we find the reciprocal of the numbers we had on the right-hand side. Okay, and then with this, we have a lot of points, and we can try to sketch that. So imagine, let's say this is 10 here. 1, 2, 3, minus 1, minus 2, minus 3. So this is 1. So this would be 5. Okay, let me try to roughly sketch that. Oh, that's going to be tough, right? Because I've got 1/4, 1/8. Well, okay, I'll just leave it like that. So when x is 1, f of x is 2. So I'm going to be here. When x is 2, we're at 4. So here, and at 3, we're at 8. So we have a function that's growing like that. And its y-intercept, as I said before, this is always going to be 0, 1. Of course, if a is, well, it's actually 0a, but a is 1 here. And after that, it becomes really small because I'm going to have 1/2 here and 1/4 and 1/8. Okay, so it gets really, really, really close eventually to the x-axis. So we're going to say here the x-axis is what we call a horizontal asymptote. An asymptote is a line that gets closer and closer to your curve, or vice versa. The curve gets closer and closer to your line. Is a horizontal asymptote. So here, as x goes to minus infinity, y goes to 0. Okay, and so the horizontal asymptote is the x-axis. It's also the same as y equals 0. So this is what this exponential function looks like. Because I'll also try to graph g of x, which is 2 to the, which is 1/2 of x. So notice that b here, this is the case. We've covered the case where b is above 1. And it's not too hard to convince yourself that for any b above 1, like 3, 4, even 2.2 or pi, you're going to get a graph that's very similar to what I have here. And at least it's going to increase as you go towards infinity and go towards 0 as you go towards minus infinity. Now here b is 1/2. So here we're in the case where b is between 0 and 1. Okay, and then we can start creating a little table again, okay, with values of x and values of g. Now, over here, this is 1/2 to the power 1, so this is 1/2. Over here, this is 1/2 to the 2, so this is 1/4, okay? And so on. After that, it's going to be 1/8. 1/2 to the 0, that's still 1. Over here, this is going to be 1/2 to the minus 1. So this is going to be 1 over 1/2, which is the same as 2 over 1, or if you prefer 2. So we have 2 here. Over here, this is going to be 1/2 to the minus 2. So this is 1 over 1/2 squared. In other words, 1 over 1/4. And this is 4 over 1. In other words, it's 4. So you see over there, we're going to get powers of 2. So 1, 2, 4, eventually 8 here. So it's basically those numbers we have here, but you flip them, right? So what has happened is that the graph of our original function 2 to the x is just flipped around the x-axis. So there's a reflection that just happened by changing the 2 to the 1 to a 1/2. But also what I want you to observe is that the graph has a kind of inverse behavior. So as you go towards minus infinity, okay, so when x goes to minus infinity, now y goes to, well, here g goes to, I can write y is g. G goes to infinity, and then when x goes to plus infinity, y goes to 0. So that tells us that we've got a, since y is going to a specific constant, y equals 0, or the x-axis, is a horizontal asymptote. And basically any point that you had previously, like for example, this point here was 2, 4, you find it here, but instead at minus 2. So minus 2, 4. So this is why I was telling you that the graph that we actually have here for y equals 2 to the, well, at 1/2 to the x is basically the graph that we have above for 2 to the x, but flipped around the x-axis. And the reason for that, and there's a good reason for that, 1/2, that's the same as 2 to the minus 1. So I can write it like that, and I can multiply the exponents together. So in fact, it's 2 to the minus x. And if you think about it, 2 to the minus x, that's f of minus x. So our g of x turns out to be f minus x. And f of minus x, this is the graph of f flipped around the y-axis. We've seen this when we were transforming functions in chapter 3. So this explains the why everything's flipped. So in other words, if you've got this curve, y equals b to the x, and you've got another one, 1 over b to the x, which is the same as b to the minus x, one's going to be the reflection of the other across the y-axis. So if you've got 3 to the x and 1/3 of x, well, they're, if you reflect 3 to the x, you're going to get the graph of 1/3 of x. So there are ultimately 4 cases for the graphs of exponential functions. So 4 cases for the graph of y equals ab to the x. Okay, I could have b between 0 and 1. I could have b above 1. I could have a positive, and I could have a negative. Okay. So let's start with top left corner, a positive and b between 0 and 1. So in this case, this is similar to what we just did. So an example would be y equals 1/2 of x. Okay, and the graph looks like this. And all the time those graphs are going to cross at 0, 1, the x-axis, the y-axis. If b is above 1, you're going to get a graph that's similar to 2 to the x. So an example of that is y equals 2 to the x. And the graph just goes up like that, and again crosses the y-axis at 0, 1. If a is negative, it just means that all the y coordinates are going to become negative now, so it's going to go like that. So it will, so depending on a, so if a, let's say, is, we can take look at an example. Okay, the minus will reflect across the x-axis. The 3 will stretch everything vertically by a factor of 3. But again, you'll have the x-axis, that's an horizontal asymptote. And similarly here, Like you could have y equals, an example, 3 times 2 to the x. It would just look like this. Oh, just realized I made a mistake. So it crosses the y-axis not at 0, 1, but at 0, a. 1 is when a is, but a is positive here, so this is why we're above the x-axis. And here it's 0 minus 0a, but a is negative, so that's why we're below the x-axis. What did I do here? Like that. Okay. 0a, not minus, 0a. Okay, so you've got all possible cases, and from this you can analyze the behavior of your function. So just to give you an example here, you could say if x goes to infinity, then y goes to 0. So that shows you that because it's going towards a constant, that means y equals 0 is a horizontal asymptote, which is the x-axis. And we can see if x goes to minus infinity, y is going to go to minus infinity. It becomes large and negative when x is large and negative. Okay, we could do this for all 4 cases. So you can actually do that if you want to add this information to your graphs if you feel like it. Okay, so next video we're going to compare linear models and exponential models in a word problem.